Okay, good morning everyone. So currently we are going to discuss momentum and forces in the context of electrodynamics. We are roughly at chapter 8 of Griffiths, and in the teaching assistants are going over chapter 9, which are applications. So you should read both 8 and 9, and next lesson we will go into chapter 10, which is discussing vector potentials and beginning of relativistic effects. So today we're going to discuss momentum in mainly momentum and forces, and we're going to introduce a mathematical concept called the stress tensor, the stress tensor of Maxwell, that gives you how forces, electromagnetic forces, act on a body. And so the second part of the course, of the lesson today, will be very mathematical. So I decided the first 40 or 45 minutes will be very physical in my mind. Maybe you don't agree. So before introducing the stress tensor and the momentum issue, we are going to discuss it very hand-wavingly and as a proposition, and not to be considered as rigorous in any sense. So last lesson we studied the Poynting vector. And to remind you, this vector pointing was given by S E cross B divided by mu 0. So for example, if I have a free wave with some frequency and some k, the dispersion is linear, it's going in this direction, for example, then we said we have the electric field, which is oscillating, the magnetic field, which is perpendicular, and then S is in the other direction, perpendicular to the plane defined by E and B. And we had the relation between E and B. This, the ratio of the amplitudes is given by C. I hope you remember this. And then this S will be determined by the product, and these two guys are waves. And then this S propagates along the K direction in the same way the wave is propagating. So this was S, but its physical meaning was, beyond its definition, was the following. S, from points of view of units, is energy, for example in joule, per unit time, per unit area. So what we think about, we have some coordinate system, x, y, z, and we have here some dA. Sometimes they call it ds, but S is the Poynting vector, so I'll call it dA. So this is an element, small element here, and there are some electromagnetic fields around. And you calculate the S here, like here, of these waves. And if the waves are going in that direction, and this is perpendicular to the wall, then you'll have a flux of energy per unit time. And the bigger the area is, the more flux you have. The bigger the exposure to the sun, the more input of energy you have into your body. Okay, this is very clear, and this is what we studied in the last lesson. So you can now start thinking, wait, if I sit on the beach and I'm getting heated, or I have a cup of water on the beach and it's heated by the sun, and the sun is some light, and the light is electromagnetic field. So what am I actually doing? I'm the light is hitting the water molecules and they're becoming hot. And what does that mean? It means that they are moving faster. And what does that mean? That their momentum has increased in all kinds of random directions maybe, but this means that light can transfer momentum to matter. But we have also conservation of momentum, right? So what does this mean, or it's plausible to think in this way? The electromagnetic field also has momentum in it. Like it has energy, it has also momentum flux. And this is an idea. And the energy, the momentum density. So, okay. So now, in this course and in previous courses, we always, many times, consider different types of densities. We have the mass density, the charge density that you learned in high school. And this course, for example, we learned about the current density, J. And last week, we learned about the energy density. And the reason is that we have energy density, we have fields E and B, and then every point has some energy, but this is an epsilon. So you look at the density multiplied by the of energy, for example, given by the electric fields last year, times delta T, delta tau, which is delta X, delta Y, delta Z, and that is in that small box, that is the energy. And similarly, we are now going to define the momentum of what? The momentum the momentum of the electromagnetic field. We are going to define it. So this is why I have this very strange calligraphy type of, because this is not momentum, this is momentum per unit volume. And the claim is that this is S divided by C squared. So the idea is, I don't know, end of semester. So the idea is that you have, okay, you see this is okay? You have here some d tau. D tau is dx dy dz, the usual notation of Griffiths, some element, and inside you have some s. S, you can think about it as the sum of all the s's over the small box, or s at the point. And s d tau divided by c squared will give you the momentum. So if you want, I can add an equation, P electromagnetic d tau. This is the momentum itself. What momentum of the electromagnetic field inside this box? And this depends on x, y, and z. So it's not like a momentum of a particle, it's a momentum which is itself a field, depending on the coordinates itself. This one? I just said in the beginning, I'm just explaining general ideas, and we'll derive it more rigorously from the Maxwell tensor. So this I'm just trying to introduce concepts and explain ideas. So I just put it on the board for now. Now we have to discuss it and see what it makes sense. So you have to believe me a bit and wait for the mathematics later. Okay? So what is the consequence of this if you believe me and you believe Griffiths and you believe other people like Einstein? So what is this? First of all, let us check the units. So this density of electromagnetic radiation units are the units of S divided by C squared. But what is S? S is, we said before, this is the energy. How do I want to write it? Let's say in joule. S is joule per over time. So let's write it as second. Meter squared, that's the area. Right, this is the S. Now here we have meter squared. That's the velocity here. Second squared. So I'm going to write this as meter to the power 3. Why? Because this is momentum density. So here I have meter to the power 4. I'm going to write it like meter. So this is okay. This second squared with this is second divided by S, and here I have joule, which is kilogram, meter squared, second squared. That's usual units of mass, and then this goes with this, and this goes with this, and meter over second is velocity, right? So here I have kilogram times velocity. What is that? Momentum. And this is then momentum per unit volume. Unit volume because this is meter to the power 3. And this is indeed the correct units at least. So you see from this unit argument that this works. And usually when you have units working, in many cases there is some meaning behind this. I mean, this is of course hand-waving argument, not a real argument. So now what is going on here is something interesting. Because you see S is what? Is related to the energy flux, right? And P is proportional to this energy flux. What does it mean? And is this surprising or is this something you should know? So the point is that we have here some linear relation between momentum and energy that you can see here because S is proportional to the energy flux, right? And is this surprising or is this interesting? So it's first of all interesting. What happens in classical mechanics for a single particle? So you all know that the kinetic energy is proportional to p squared. Here, it's not like this, because we said the momentum is proportional to the energy, and the energy is proportional to the momentum. Yeah, 1 second. So is it surprising or not? I don't know if it is surprising or not, but you saw this somewhere. You saw it actually also, you know, some experiments on this. And you saw it both in quantum mechanics, I think, more specifically in the photoelectric effect that Einstein analyzed. So what does Einstein say? What did he say? You have a system and you shine on it light. What is this light? This is a famous equation which I assume you know from the photoelectric effect. This is h bar omega. Of course, in our course there's no h bar. Don't worry, I'm not going to start electrodynamics with quantum. So it's h bar omega. The h bar is not my point here. But what is a h bar? I mean, what is the frequency? The frequency is c times k. And this is c h bar k. But what is h bar k in quantum mechanics? That's p. So you see here that this experiment says that you don't need here h bar. I mean, it says c times p. So you see that this is a linear relation between energy and P. But what is this, when you think about the photoelectric effect, what are we shining? We are shining light. Well, what is going on there is something is falling on the material. What is this material? What is falling? What is the light? Composed of photons. Photons are most mysterious objects for you until you go to second degree, because you don't see really photons. We imagine some particles which have no mass, right? But hitting, and this is what is going on, and then you see this linear relation. You also see it in mechanics, but relativistic mechanics, this linear relation. Okay, this is, let's call it classical in the sense of Newton. In usual classical mechanics, we have E squared equal, if you know this good, and if you don't, ask for your money back from whoever taught you. This is a famous relation between the energy of a particle, its mass, and its momentum. Maybe you saw it in different ways. You can also write it as E equal mc squared square root 1 plus p squared mc squared. Did you see this equation somewhere, let's say in a bar or somewhere? So now what happens, let's say from here we can reach two well-known limits. One of them is the mass is 0, which is what we call photons, which have no mass. And if the mass is 0, the rest mass is 0, then E is equal PC. And again, the emphasis here is the linearity between energy and momentum, which you also see here. Of course, the real story is completely the opposite. This was first, that was second. But at least this is something that you can more or less understand, and you can start thinking of, how to measure these type of things. For example, by K, or that would be quantum, but other methods. Simply said, what does it mean that the field has momentum here? if I in principle put here a particle, you can transfer the electromagnetic momentum to the mechanical momentum, and then you'll move. So it's real momentum. You can really, if you can transform you can transform it into mechanical momentum. But the second well-known limit is that when P over mc is much smaller than 1, and then the energy is given by mc squared, which is the famous mass, the energy of the resting mass, the famous constant that usually it's not important unless you want to build a bomb, plus p squared over 2m. And then there are more terms, correction, so this is what we call kinetic energy of a classical particle. But again, if the mass is 0, then you cannot make this assumption, right? And this assumption when mass is 0 is impossible. And this is exactly the point, that these photons or these objects or these fields, you cannot treat them as in any way, even if you want, as something classical. That's the idea, and this is the meaning of this linear relation that we have here. Yeah, what is the question? Good. So, can we make it slightly more hand-wavingly precise? You can have the following argument. Again, it's an argument, it's a proposition, it's not anything real. You can say the following, and now I'm going to use the speed of light in this argument. I'm going to build I'm going to build this box, and this box has some area A, and let's say there are electromagnetic fields going in this direction. And let's say, just for the convenience of discussion, that these objects that are moving inside here, that are transforming the energy and that they are transporting the momentum, let's say they go in the speed of light, c, which we know is true. These are the photons. So we have here c dt. What is c dt? If I look for this time c dt, all the photons that began here will cross this area. If they started this distance, they started here, they have velocity c, they will cross this distance a. So we have something that is going through this a. Now what is going through this a? All the energy density that is stored inside this box in this delta t. If delta t is bigger or smaller, then more or less will go through, that's obvious. All this energy will go through this a. Okay? So we can calculate this energy. This energy is, first of all, u dv. What is mu? What is mu? That's the energy density. And I'm assuming here the energy density is constant. So inside this box I have energy per unit volume, and the volume of the box is delta V. And then the total energy, if the velocity is c, is going to go through this. This is the energy that will pass through it. And we know that this dE is related to the vector pointing. So eventually I'll connect this energy to the vector pointing, obviously, but this is also U times A c dt. So what is this? This is the delta V, maybe volume, the small volume that I have. So I just write here the total energy. But we know that, hand-wavingly, that delta E divided by dt times A, this is the S. By definition, the total energy passing in a delta time t divided by the area. This is what we said before. This area, this is like this delta A here. This is exactly the S. So this is equal UC. So this is another way now looking at the energy density is S divided by C. And you can read more about this if you want in Griffith's book. Now we go back to the second what we had here before, that energy is proportional to PC. So we have inside, we assume linearity. If we assume that, then we immediately have here that the energy density and momentum density are also proportional up to a constant c. And then from these two guys, what I get is that the momentum density is S divided by C squared. And this is what I claimed over there. And here I'm doing it sloppy, so let's say this is just the units. So this is the general argument. So what did I do here? I said there is an energy density. I said this energy density has to be proportional to the momentum density, because energy and momentum are linearly related. And I did another thing. I assumed that things are moving here at the speed of light, see? And with these two assumptions, then you can ask those assumptions, are these correct or not? That's a different story. But with these assumptions, I got this kind of hand-wavingly, I got this object here. And if you don't like this, then okay, we will study this more seriously later on. But this was just an introduction for you to think about, because what is going on here with the energy and momentum is rather deep, in my opinion. So we better start with simple things. So now, so now let us assume that this equation holds, and then to show you how non-trivial it is, I'm going to discuss some idea that Einstein had on this issue. And most of Einstein's, when he was like younger than some of you at least, not that Tudaim, yeah, so that Tudaim have still chance to become like Einstein. Not really. But when Einstein was young, so okay, a lot of his methods were not like traditional methods that you read in books. This came a bit later, but he had a good imagination and arguments. Of course, this was a problem, because if you come with a lot of arguments to all professors, especially at the beginning of the 20th century, they just kick you out of the door. So he had to work in some patent office. I think you know this story. Because what was he talking about? And if you have the same feeling here, then it's good, because then you are like the old professors at the beginning of 20th century. So don't worry about this too much. It's more for you to start thinking, not for you to accept this. Okay, so what was Einstein's idea? So let us start with something classical that you know. Let's say we have a cowboy or cowgirl inside a carriage with no horses, with no engine and nothing. And this guy has a pistol, and he shoots a bullet. This is a bullet. What will happen to the carriage? It will go in the other direction. This is all classical. You know all this. So we have a system at rest. There is momentum of the bullet in that way. The carriage will go in the other direction. Now we said just now that when you have light, the light also is somewhat similar to the bullet. If you can generate some S here in this direction, then you are going to have a momentum in that direction, right? It's like the bullet. So what is going to be the bullet here? You're going to electromagnetic bullet. The guy here will have a torch, and he will turn it on. Then you have light, electromagnetic field, and it's going in that direction. And then, okay, if you do that, what will happen to the carriage? It will go in the other direction from conservation of momentum. So conservation momentum is holy. The reason why conservation momentum is holy is that it is related to the fact that the space is homogeneous. You don't want to violate that, or Einstein didn't want to violate that. but he could throw away many other things to the trash can. So let us see first what happens to the bullet and to the bullet and the carriage. The carriage is more interesting for us. So the idea is that we have something equal 0, and that's the center of mass of this object. This is one way to look at things. And then we define m of the carriage. Wait, m is the carriage or everything together? Yeah, plus bullet. And a small m is the bullet. So what you think about is the following, that it moves, but then it will be absorbed here on this wall, right? And eventually, we are talking not about the process, but what happens eventually at the end when it's stuck, how much this carriage would move. Then this is the following, then this is equal to delta x of the carriage, m minus m, plus m of the times L, I'll soon define L, but it's obvious, divided by m. So, and I'll soon show you this, and L is simply this distance, L. How far you move. And then m is much bigger than m, then you get that 0 is equal delta x carriage plus mlm. So the motion of the carriage is related to the ratio of the mass times the length that you had here. Now this, if you don't know, like this type of argument, you can do also from conservation of momentum for classical particles. It's exactly the same, because we can write, okay, m is the, m here, okay, so yeah, here I made an approximation, right? I left this small m out, because the carriage is macroscopic and very big, and I throw away the bullet compared to the macroscopic, and then this is a small number. So now I'm going to do the same approximation, m times u of the carriage. So the approximation here is again that m, the small m is not important. So this is the mass of the carriage of the whole system, is actually the mass of the carriage. Just to simplify, this is m v bullet, right? This is simply, at the beginning there was 0 momentum, and then the carriage has this at the beginning, not at the end.
Doesn't it supposed to have a negative sign on one side?
Yeah, but I put it on the other side. The total momentum is 0, and then I put it on the other side. So the momentum of the carriage is equal to the momentum of the bullet. When you started, you didn't shoot yet, you go like that. The total momentum is 0, you shoot, boom, and then the other guy is going in the other direction. No, there's no missing minus. This is just, first of, no, there's no missing minus. We understand the direction. This is not our problem. It goes in that direction. So yeah, minus. So we have the u carriage equal, this is well understood, this is just the magnitudes. And then we can say that u carriage, the velocity of the carriage, this is not energy density, of course, is the ratio of the mass v bullet. And then forgetting about small details like acceleration and all these things, which means that the L is very big and you reach the finite velocity very quickly. Einstein wants to argue that what is the velocity of the velocity of the bullets? Okay, so we have. Okay, sorry. So this is okay. Now we want to know what is the delta x absolute value of the carriage. So this is the velocity of the carriage times what? Times the time, right? Time that you moved. But what is this time? This u carriage is simply the time that the bullet was flying. So this is L divided by V bullet. So, but U divided by V, if you put it here, this is equal M over M times L. So, but this is exactly the same that we had here. So why did I do this again? Because usually you think about delta X as increasing maybe with time, but here it's L because it stops here, that's all. So I'm just pointing out that simple conservation of momentum gives you the same argument that you have here, and it's obviously related because the reason why the center of mass is not moving is because the total momentum is zero. So this thing and that thing should give the same results, and indeed they do. But now we have now we want to do something more intelligent, the cars, and that is we want to we want to look at this as now we're going to do something else. We want to do it with electromagnetic momentum. So we have the guy standing here and he has this torch. So now we have a torch. And what he does is the following. This is a time t equals 0. And then this guy, at some later time, the torch is turned on. So you're not turning it on immediately, you are turning it on and you're waiting. This is where the light is. It's spreading like this in the speed of light. And then eventually the light, the first light that was emitted will hit this wall. You are still generating, and then you turn off the torch. Turn off the torch. So what did we do here? We turned on the torch, we created electromagnetic radiation. There is momentum transfer and energy transfer to the other side. Then what will happen? The carriage will go the other way. But it's very, very weird. Why is it very weird? Because the mass of the photons that we had here is zero. So this is actually a paradox. It's not for Einstein it was a paradox because the mass is zero. So here we have transfer of momentum. So this is a problem, and we assume that the center of mass, Einstein could decide, let's throw this one away. No, but he doesn't want to throw this one away because that is momentum conservation of the total system. So how do we reconcile this? Well, we don't, but Einstein did. So what is the idea? Let us try and calculate now with the equations that we had before, very roughly. This is not a serious calculation. Back of the envelope calculation. Let us try and reconcile this. And so the electromagnetic momentum density again, this is momentum density, is S divided by C squared. And this is the vector pointing. So what is the delta X of the carriage? This is the momentum. I'll write it down and so you'll understand. Per unit volume. What momentum? The momentum of the electromagnetic field. times the volume what is going to be the volume, the total volume that you are transferring? It's all this volume here. That is the total momentum that you are giving, times, what does this give you? That gives you the total momentum, and now Einstein divided by m of the carriage. That is, he's treating the carriage as totally classical. So this is simply momentum of a volume times volume is momentum. Momentum divided by the mass is velocity. Velocity times t, like high school. You see, it's like high school. It's the same thing. So this is velocity times t, and this is what is going to on. Now, what do we know? We know this guy, and we can calculate this volume, right? So
The volume is the volume of the carriage or the volume of the light beam?
no, the light beam, because the light beam is containing the electromagnetic radiation. Yeah. So this light beam, it has some. You think about it as a tube. It has some A. This A eventually is not important. You can see this more or less because in S the energy is related to the size of this thing. It will eventually not be important, but there is some A defining this tube, and there is this distance as before is going to be L. Okay, so think about this as a tube, and you have an area surface, and you have this wall. So now let us see what this is. So this delta x is 1 over c squared times s. That's the momentum per volume. This is this equation. I just put it here. Times the time divided by the mass, times L times A, that is the volume. All right, this is the volume of this object here, this light beam. Now let us organize it a little bit. You have SAT, here I have the mass, c squared. Oh, this is nice. What did I left out? T. No, T I have. SAT. I have here still L. Now, what is SAT?
The energy.
The energy that you transfer. This is previous lesson. This was my introduction. This is the energy. Now Einstein is very wild, and he says like this: delta x, because what we had before of the conservation of the center of mass argument, it must still somehow work. But we don't have an M. This is a very brave thing to do. That's why I didn't get the job. M effective, we're going to write this as some mass effective, and we'll soon think what this means, times L. And this thing and that thing should be the same. Because here you have this awful L, which is non-universal. It depends on, it's not something worthy of a real good theory. It's just something I put in that I have to throw out. But this is equal energy, again, of the electromagnetic radiation, times L, times mc squared. So if I cancel this, and then I cancel this, then this energy, again, what is this? Let's emphasize, energy of the electromagnetic radiation that came out of this thing is equal to some m effective c squared. This is how he argued from his famous equation, not through anything related to mechanics or anything like that. He gets this famous formula that energy, what is this thing? I'm not saying what is m effective yet. This is the beginning of some big revolution. It's just saying that energy is equivalent to mass. So it's an equivalence principle. Inside the energy, there is some mass. Later, people had to prove this. You know that it was proven and what it means. Now, what does it mean for light? If I have the light and I turn on the light, will the mass of all the system will increase when you have more and more light? The answer is yes. Today, we believe that the mass, the inertial mass, not the gravitational mass, will increase. And if you have more energy by generating more and more photons, yeah, the mass will increase, and it will increase by this amount. So this is not a gravitational mass, but it is physical in the sense that you can, from the point of view of inertia, let's put it this way. So, okay, so here we got this famous equation, and now what we're going to do is, let us have a break, and then we're going to, let's have a break for 10 minutes, and then we'll start the math, and we'll grind the math till the bitter end of this class. So now we are going to discuss Maxwell's stress tensor. And it deals what appears at the beginning as a very simple problem, and that is you have some body, and this body has charges, and it is put inside the electromagnetic field, and then you want to ask what is the force acting on this body. This is not a point charge, then it will be rather easy, but this is a real physical body, and we want to calculate the force on it. So the setting is the following. We have some body. So I'm going to call it body. And inside we have some charge, which I'm going to call J, and there is possibly some current J. Now far away there might be other currents, J1 and something ρ1. These guys are creating electromagnetic fields. Maybe a complicated way. Of course, in exercise it will be very simple. And you have here some electric and magnetic fields, E and B, created by these things. But we don't care about the other charges and other currents. Mostly we don't care. We created these fields. Now, this E and this B is acting on this body. And there are some complicated currents inside, and there are charges inside. So if I look at some element volume inside here, some delta tau, there is some velocity field, and the magnetic field will cause it to move somehow, right? And there is an electric field, and if there are charges inside here, so what we need to do is we need to integrate the influence of all the forces over all the body in order to get the force acting on all the body. And how do you do that? In principle, this is rather simple. We just need the force. And what is this force? This force is related to Newton's equation. So I assume the body is classical. It's not a very light particle, and the total velocities of this object are small. So F equal ma, like high school. This is the force on the body, and this force is given by a volume integral. What is the volume? The volume is this object, the body itself. I integrate over all the volume over delta t, etc. And inside here I have E plus V cross B times delta tau times rho. So I think this equation is well known, but I just wrote it a slightly different way than you used to. So V cross B gives you the magnetic field, the force of the magnetic field, and what is dt times P? That's simply the charge. So this is Q VB, V cross B, right? And this E here times, this is the charge, delta Q, E times delta Q. And we need to sum all these forces in order to get the total force acting on this body. Okay, this is simple, and it's fine. I mean, in principle, you can do this. But the idea is, related also to what I said before, we said the electromagnetic fields carry momentum and energy with them, and energy and momentum is translated into force. That's the second law, F is equal dp dt. So we can rewrite this and get and eliminate rho and v eventually at the beginning. And our aim is to rewrite this force totally in terms just of the fields, E and B. I want to eliminate. Then if I know the E and B, then I can calculate the force exactly. What is the idea? What is rho? This is something simple. If you know Maxwell.
Epsilon zero times the divergence.
So I can replace, for example, rho with div E. And I can replace, okay, what is going to be V times rho? That is going to be the J. And where does J pop in? In Maxwell, in Ampere Maxwell law in Newton. So what I'm going to do at the beginning, I'm going to just replace this and transform it to something else. And this thing at the end of the day, if you don't fall asleep in the middle, will be related to the vector pointing, to the energy density and all these things. And these are eventually going to give you this F. Okay, that's where we are heading. Now, there is another issue, and that is, what are we doing here? Why is this maybe not so pleasing? I need to go inside the body and find the magnetic fields and the electric fields, etc. Now, if I know them, fine, I can calculate, maybe I can use this equation if I know all these objects. But in most situations, you don't know these objects. Because simply, let's say from a point of view of measurement, how will I go inside the body and say what is the electric field inside the body, right? Do you know how to do this without opening it and breaking it, and then it's not so good? So we can immediately start thinking about this, and I can add here an integration path like this. For example, I can do it many ways. This is a second integration over a volume. The point here is that the density here is zero. The density inside the body is not zero. So I can extend the integration volume. This will not do anything here. It will be actually very stupid because rho is zero, so I didn't do anything. But if I replace this with the electric field, what will happen at the end of the day, I can, let's say, measure the electric field here and magnetic field here in order to infer the force here. That is going to be the general idea. We're going to also change the volume integral into a surface integral, all these things. And eventually, at the end of the day, my hope is to show you that if I measure the electric and magnetic field here, I can tell you what is the force on this body. Now, what is the electric and magnetic field here? It is created by two things. The body itself is creating electric and magnetic fields here. And whatever created. So this effect is not only related to the electric and magnetic field created by these two guys, but also by these guys. And that will create a complication and another thing that you need to think about kind of deeply. Okay, so this is what I'm going to do, and this thing will lead us to something which is called Maxwell's stress tensor. And this stress tensor has in it things like pressure and shear that we will try to understand what this is. So there's a lot of new words here, or not new, I don't know, but there's a lot to learn, and you should read very carefully in the, wherever you read, I don't know. So first of all, the zeroth step, let us define a force per unit volume. So I just take, you see I have here this delta tau, that's delta x, delta y, delta z. So the force per unit volume is, so again, this is force per unit volume. to get a real force, I need to integrate, as I did here, over delta tau, over the body itself. And this is simply equal to rho times E. You see here the usual charge times E divided by volume. This F is a local point. It's a local point in space, right? It's not a global force. Plus J cross B. And what did I use here? I used here this. You see V times rho. This is, by definition, this is this J. The J, which is the current density inside the volume. Okay, so now I'm ready to write, as mentioned already, this law, which is Gauss, which is Coulomb, which is one of the Maxwell equations. So I can replace this rho with this object. And I can also write J as rotor B. You remember this, I hope. Maybe you don't remember if the U0 is down or up. I always forget. This is ampere. But there is the correction, the famous correction of Maxwell, minus epsilon 0 dE dt. So this is ampere Maxwell. So we used 2 of Maxwell's equation up to now. How many more do we need? 2 more, which are Faraday and div B equals 0 that we will use later. So if I use all this, I can write the force per unit volume inside this volume in an ugly form, E0 div E times E. Again, this is simply rho. This is this rho E. And now I had one term, now I'm going to have 2. So the level of complexity went up a little bit, and it will go more and more, don't worry. So it will become much worse. So then I have here, I just copy rotor B over U0 minus E dE dt. All this is simply J cross B. Where does this cross come from? From the definition of a force on a velocity particle with, this is like in high school. Okay, so this is this F. Now, what we want to do, or what Maxwell wanted to do, is we have E and we have B inside here. So already we made some advance in the sense that if I integrate this, I don't need the, I don't have V and rho inside. Of course, this is not enough for us. We want to do more. But we see here expressions that contain E and we contain B. Let us try and make them as symmetric as possible. That E and B are treated in the same way. That is what I'm going to do now. So how to do this? Okay, so how to impose the symmetry? So first of all, let us look at this term here. We have dE dt cross B. Now, we didn't use Faraday, right? But Faraday, what does Faraday demand? The change in B, right? Because you remember the experiments of Faraday, you change the magnetic flux. So you want to move this derivative to this one. How will you do? And then you can use Faraday. How will you do that? Let us write a simple identity, ddt E cross B minus E cross dB dt. So you see the time derivative of this multiplication, it's the chain rule. You take first the derivative of E here, and then the derivative of B. This is this one. I just organized it a little bit. Usually this guy is on the other side of the equation. Now I'm very happy. Why am I happy? Because if I know Maxwell, because I taught you, what is this E cross B? Up to a constant. This is the pointing vector. That is maybe interesting, maybe not. And what is dB over dt? What is it related to? This is related to Faraday. So now I can plug in Faraday into this term, and you see we started with 2 terms, now we have 3, now we have this term, and this term will be 2, so we'll have, it's not yet, it seems that it's going in the wrong direction, but it's not. Or maybe you think it is, this I don't know. So, yeah, so let us just plug in Faraday. So, okay, so reminder, what is this thing? This is cross E, right? dB dt this is Faraday. Then we have here something very ugly, E cross curl of E. This is what we get out of this guy. So if we do all this together, then we are at this point. I'll just copy from my, yeah, let me copy. Yeah, so, okay, E0, div E times E. This we remember, this is simply the row here that we had at the beginning. Now we have this crazy E cross curl E. So it turns out with a minus sign, cross curl E. So this came from the Faraday, and from, yeah, by changing and from here, plus or minus 1 over mu 0 B cross curl B. You see it's here, cross B. This is from ampere times B, but I did something. I switched the order. And that's why you get, from this plus, you get a minus. You see, why did I switch the order? Because I wanted it to be the same like what you got here from Faraday. I just switched the order, you get a minus. Minus epsilon 0 ddt, more or less the pointing vector. Now, we said this is related to momentum, right? This is what I argued before. So you see what is happening here. What is this f if I integrate over a box, let's say? So the integral over the f, what is it? You know this from high school. It's the change of the momentum of the body. But this, you'll have here a new term eventually, which is the momentum of the electromagnetic field. So what is happening here, the electromagnetic field has in it momentum, and if it changes in time, like in Newton's equation, it's transferred to the momentum of the body. This is the beginning you more or less see with this d over dt, which has, it's the same like in Newton. The change of the momentum of the electromagnetic field has to go to the momentum of the body. And this is the beginning, and again, you need to think about it more, why I called this before momentum density. So you start seeing this, maybe at this stage. Okay, so I have this F per unit volume. Now, I look at these two terms, and they are not, here they are equivalent, E and B. Here they are not equivalent. This guy and this guy is equivalent, but I don't have something like this. What shall I do?
You can add it.
I can add it. And why can I add it?
Because the divergence is 0.
Exactly. So, you see, it's very easy. The div B equals 0. This is the fourth Maxwell equation. So we used all the Maxwell equations up till now. Yeah, there's no other Maxwell equations as far as we know. And I can add here a term like div E. I can add here a term div B multiplied by B, and then it will be symmetric. I'm symmetrizing things. So And then if I summarize then all this thing, I get this lovely equation. F equal the following: epsilon 0 div E. Again, this is simply the density times E. Okay, yeah, one second, I forgot. So now, of course, we are left with these crazy objects. For example, this object. And we also have B cross B. But this guy, this is a mathematical statement. This guy is equal to 1/2 delta, there's only one derivative, E squared. E squared is EX squared plus EY squared plus EZ squared. This is a vector plus E dot E. Again, this is a vector with one derivative. So this is just a mathematical identity. What is this E squared? What are you reminded of E squared? What is E squared?
It's the energy in the electric field.
Not energy, but
Proportional.
energy density.
Energy density.
But this is the energy density, and you see that this is nice because you have the derivative of the energy, and this is like when you solve classical problems, the derivative of potential energy gives you a force, right? So here we have something similar. The derivative of an energy density starts popping up here, and you have here only E, but I have also this term, which I can do the same thing, right? I can, I'll get the derivative of B squared, but then there is also this term that we need to think what it means. So,
Cancel.
what do you mean cancels? No, it doesn't cancel. You would be lucky if it would cancel. Generally, it doesn't cancel. If you mean that these cancel, this is not true. E plus 1 over mu 0 div B, which is 0, but I still add it, B, so this is 0, this is raw, the rest comes from the math, plus B div B minus half delta epsilon 0 E squared plus mu 0 B squared. This is the energy density. Energy density at a point, energy density. Minus the essentially the vector pointing. So okay, this term is still a mess, and we need to think what it means. This I'll call equation A, Aleph. So now we need to stop and we need to define something. We'll define it and then simplify this, or this object is called the Maxwell stress tensor. What is Maxwell stress tensor? It is essentially a 3x3 matrix. And this 3x3 matrix reorganizes all these terms, and the elements of the matrix, 9 elements, they have physical meanings. Some of them are called pressures on the diagonal, and on the off diagonal they are called shears. Shears means if I take something and shear it like that, like pull it like that, and instead of forcing it from the above. So it's not going to be so beautiful, but let us just write these definitions, and then later, through exercise and a lot of thinking and ChatGPT and Claude or whatever, you may understand it, or you may leave physics forever. So I'm going to define a matrix. The matrix has 2 indexes, which are I and J. And I and j correspond to the x, y, z coordinate system. So the Maxwell strength tensor, I'll just put it on the board, Tij, this is I, is equal to the following thing. Epsilon 0, Ei, Ej, minus half delta Ij, E squared, which is the three elements together, plus 1 over mu 0, Bi, Bj, minus half delta Ij, B squared. This I'm going to call equation bet. So what are we actually trying to do? You see here, in this object, in this f, I have the derivatives, the spatial derivatives of E. Here I don't have any spatial derivatives. Eventually you'll have a derivative of this guy. But this in some sense will be like a potential, in some way that it will be clear that you have a potential, the derivative of the potential is the force. And this Tij is an object like, but more complicated, like a potential. When we take the derivatives, we will get this force out. I'll show that a little bit later. So, but let us just focus on this object. So first of all, what is I and j? As I mentioned, this is x, y, and z. These are the directions in space. So every point in space, I'm somewhere in space, x, y, and z something. You have some fields, and then I have these things. So for example, let us write, okay, this is x, y, z. So what is tzz? What do I want to give an example? Txx. So this is epsilon 0, I is x, j is x. This is ex squared minus delta ij. What is delta ij? This is the Kronecker of delta. It's equal 1 if I is equal j. If I is x and j is x, that is just 1. Minus half. What is this e? This is ex. And remember, ex is the field in the x direction, which depends on x, y, and z, and in principle also t. So this is depends on, in principle, on 4 coordinates. Y squared plus ez squared. Plus magnetic terms, which are identical. So you see what happens here with the half, this minus half and this plus half. So this is epsilon 0, ex squared. The half can come outside. Minus ey squared minus ez squared. Plus 1 over mu 0 bx squared minus x is because I chose the indexes as x, minus by squared minus bz squared.
You need the half.
Yeah, the 2 here, and then like the 2 here. Now we have this matrix, and again, these are statements. I'm not proving yet anything. I'll slightly prove later. And then you can multiply this matrix by by vectors from the left and from the right. And for example, this is the usual definition A. So by the way, this T is sometimes written like this with 2 arrows, this tensor, because it's not a vector like E, right? E is a column vector. This is a matrix, so it has this double notation. What I'm trying to say that when I multiply T, for example, if this is notation dot dA, for example, later when I integrate, what am I doing here? I'm multiplying a matrix, because this is a tensor, by this dA, which is a vector, and the result is still a vector. So we don't want to have here, so this is a notation, notation if you want, that reminds us that T is a tensor or a vector. So, sorry, a matrix. So if we have some vector, this is A, times this T, it has three elements, X, Y, and Z. So I have some element J, one of them. And this is simply sum AI T Ij. And we still need to understand what is Tij. Don't worry, I'll try to explain it briefly later. X, Y, Z. So this is the sum, and then if J is X, then you have one sum. If J is Y, you have a different sum, etc., etc. So there are three components of these guys. So this is the definitions. Now Maxwell's claim is the following, and that's why we prefer Maxwell's tensor on this ugly thing. This is not physics yet. Maxwell's claim is that F, the same F that we had here, that is the force per unit volume on some small volume inside the body, this is equal to the divergence acting on T. And what does this mean? This means exactly this. When you change this A is some general vector. So what is it here? A is d dx in the x direction, d dy in the y direction, d dz in the z direction. This is the meaning of this guy. Minus epsilon 0 u0 ds dt. So what do you see already at this stage? What you see is that the force is combined of two things. This everyone can see. And one of them is this div acting on a tensor, which is, in my analogy, it's not exact analogy, what you learned in high school. You didn't learn anything between high school and this course. I'm kidding. So this is the derivative, like a spatial derivative of potential, but now you're not doing it on a potential, you're doing it on a tensor. This is like a force. Think about all the fields. Let's assume all the fields E and B are independent of time. This remains. What about this guy? It does not remain because it has a derivative with respect to time t. So the accomplishment, the mathematical accomplishment is we first calculate this t, this matrix, and later we take this derivative. Derivatives are quote unquote easy. They are not, but this is the idea. This will be present even for static fields. But then in addition, we have this thing. S again. What is S? S is the Poynting vector, E cross B divided by U0. I just took it from, this was easy here to take it from here. And the definition, this one is related to the speed of light. And what is this? This, how we interpret it, is the momentum this is what we said before. What is S proportional to the momentum density of the electromagnetic, we call it electromagnetic field, and you see why. Because this F is related to the mechanical energy, the mechanical momentum change according to Newton's, and according to Newton's law, you have here this coming from the electric fields, and this momentum is fed directly into this dp dt, and both of them have this dp dt because of the second law. Essentially, you need this time derivative to transfer into force, because force is equal to change in momentum plus the forces that are acting on you, right? I mean, this is the general idea. This is why we call S the momentum density. This is more or less a proof. But if you don't like this proof, it's just words, you see now the precise meaning of this. This is, from here came the ideas of Einstein to say this S is like momentum density, etc. And then go to light and all these other things that we had before. Okay, but now we want to go back for a second. Let's go back for, so this is the main one of the main. It's not the end of the day. This is still pretty nasty. But you have here a divergence. Now, what is the next steps? The next steps are what we need to do to calculate the total force on the body. We need to integrate over the whole volume of the body, and we are allowed also to integrate over a bigger volume as long as there are no charges inside. And we like to integrate over this thing. Why? Because it is essentially integration over a derivative. It's like in high school. So, no, it's not, but this is the divergence theorem. You see it here. When I will go to a full body, eventually the forces inside the body will not be important because I'll integrate over the volume, over the surface, not inside. And the surface cannot be not only on the body, but it can be also far away, because of what I said. So this way we will soon come. But now the question is, why is this T giving you this thing? So I guess in my imagination that Maxwell thought about this, and he found this relation simply by very hard work. But maybe he was much cleverer than what I think. Usually it's with hard work and then you are clever, not the opposite. Unless you are Einstein, and then it's just imagination, but that's a different story. That's not, I don't know, okay. So, how do we look at this? I'm not going to prove it because there are so many terms in this thing. I'm not going to prove everything, but let us look on Fz. So this is the force in the z direction. So you see this F has a component in the z direction, in the y direction, in the x direction in general, depending on the fields. We just want to look at the s direction. So this guy, I'm going to use the thing that I just now killed. So Fz, if I take the definition of the derivative, so you see it here. You see here delta div times t. So this is like my a, and this is my t. And now I need to use the equation, it's really the usual thing of a multiplication of a vector by a matrix from the left. But now the vector is derivatives, right? That's the only thing. So this guy is simply, by definition, d dz tzz plus d dy tyz plus d dx txz. So this second index is the index that I'm choosing the component of the force to, and then I need to sum. You remember the sum of the AI, you have here three summations, and the a's with derivatives. These are these three derivatives that we have here. This is the definition of the force in terms of this matrix. And the matrix, again, the T is, you have here, it's Txx, Tyy, Tzz, and here I have Txy, here I have Txz, Tyz, and this is, by the way, a symmetric matrix. A symmetric matrix because of the definition that we have here. You see, if I switch EI and EJ, I get the same result, and the same with BI and BJ, and B squared doesn't care about this thing. So essentially I have these diagonal elements, which I'm going to later say these are related to pressure, and these are called shear. But those guys that are on top are the same as those that are on bottom, because this matrix is both symmetric and real. So this is the force according to the claim. And let us look also at this thing here. So let's look at Aleph first and see that it is the same thing. So what will I do? Okay, let's take b equals 0, because this is too much. And also because it's symmetric. You don't, if you nearly solve it for E, you solve it for B. And if b is 0, then of course also the vector pointing. So what I have here is 1, 2, 3 terms only, but these are not sympathetic. So I'm using Aleph, so Fz on the other hand is equal epsilon 0. Yeah, let us write it in the full glory. I'm not sure I want to do this, but I'll do it because then you'll appreciate, not me, but you'll appreciate Maxwell maybe. Plus E dot E minus epsilon 0 over 2 ddz E squared. So you see what I'm doing here. This is this E squared that I have at the end, and I'm taking these two terms, and the rest I say for simplicity as 0. Okay, what is this thing? This is equal epsilon 0. What is div E? Okay, then it is d dx Ex. Sorry, why don't you correct me? I want it in the z direction, right? So I'm going to use, this is the whole f in fact, so I'm going to use it here only in the z direction. So this is E. Yeah, so here, yeah, okay, so let me write it down. So this guy is Ez, this is a mistake, and this guy is Ez. You see why? Because the direction of the vector f is given by this one and this guy. So I'm in the z direction, so here I have div E is a scalar, that is actually rho. E is a vector, and I want to go in the z direction, so I take here the E as being the z. And when I take here the derivative, the div of this squared, I mean the, yeah, in the z direction.
But in the second term, don't you need to use the first E as the Ez because he's the one that
no, because it's E dot del. So this is Ex, the derivative with respect to x, Ey, derivative with respect to y, Ez with respect to Ez. I'll write it down and then you'll see. So I have here the following. Plus d dy Ey plus d dz Ez, all this multiplied by Ez, plus Ex d dx plus Ey d dy plus Ez d dz multiplied by Ez. Again, the z is because of the direction that I'm working at, minus epsilon over 2 d dz Ex squared plus Ey. This is E squared. Remember, this can depend on x, y, and z in time in principle. Only there's no time here, but this is this thing.
But the Fz that we wrote at the top, it's for a constant time, right? Otherwise, we
No, there's no time. There's no time. Well, there is time, but there's no magnetic field. But okay, think about it. There's no time.
Okay.
Oh, so now I need to use again this equation and see that this is the same thing. And okay, you can do it, and you'll see that it is a big mess. But yeah, okay, so here it's too much. So let us look at the derivatives with respect to z only. So these are the derivatives with respect to z. I'm not going to look at the derivatives with respect to other values. So this is dy.
No, it's less.
This is z. And this one also. And these guys should give you the derivatives with respect to z here are these guys. right? Because the other derivatives with respect to z do not exist. So if I still work here, so let us look at this. Take the derivative of z, of tzz. Yeah, tzz. This is the derivative. Where is the definition of t? Oh, here, up here. So this is the derivative with respect to z of epsilon 0 I can put out. Then I have ez squared. There's a half minus, you remember this, ex squared minus ey squared. Because this is going to be 1. You have the half, which will kill the half. The first guy will be squared, half, and then you have these half outside here. So this guy, if I didn't make a mistake, is epsilon 0 over 2. This is 2 ez ddz ez minus 2 ex ddz ex minus 2 ey ddz ey. And these should be, if I didn't make, so first of all, the 2 and the 2 and the 2 and the 2 go away. So look at this term, for example, it's epsilon 0, derivative of ez, ez. So this is the same as this one. So this one and this one go away. It's the same thing. So here again, I did it by the first definition by equation aleph. Here I did it with respect to the new definition. And here I have wait. I made a mistake. No. Wait, did I make a mistake? No, wait, I made a mistake. I made a very bad mistake. Wait. Yeah, oh, okay, sorry. So, yeah, I made a mistake because here I have 3 terms. Let us look at this term. Sorry, let us look at dz ex squared. So let's call this 1. So I have dz ex squared, then I put the 2 in the front, then I have the derivative with x with respect to z multiplied by x. This is this one. Similarly for the y, I have the derivative of z with respect to y, I put the 2 down here with this minus sign, that's the whole important thing. So this is 2 and this is 2. Do you see it more or less? And then I need to be a little bit more careful than what I was, because you see this is going to be 1, and here I have this term and this term and this term, all of them together. So sorry. So 3 and 3. So here I have 1 term, and then I take the derivative with respect to 2. It will kill one of them, and you are left with only one of them. And that's why you have here 2 over 2, that's 1, and then I'm happy, but this is 3. So 3 comes from 3 contributions. So what I just wanted to show you is that physics is not necessarily beautiful, but all this math gives you a simplification. So after you prove it once, you don't need all this kind of junk. And instead you know something much simpler, t. But to prove it, you need to go through all this math and see that it is correct. So life is not always like what Einstein is doing. You need to prove things, and a little bit of work. And today is very easy to prove this because you just ask ChatGPT to check that this is correct. Of course, Maxwell had to think more because he had to first find t and then prove that t is giving the correct thing. Okay, so now we have some mathematical insight. But now, what we're going to now do is, what the hell does it mean, and give some examples and try to understand the physics. So maybe we have now 10 minutes break again, even though I usually don't leave a break, and then I'll come and try to explain what is the meaning of Tij, how do we use it, and simple examples to get some insight into this, okay? So let's have another 10 minutes break, so...
כאילו לימוד בתואר.
זה כן אבל היה מוכר. כאילו היה...
אתה רוצה אני רציתי שתחזיר לי את המחמוד.
Okay, so we derived this equation that gives you the force at a point x, y, z, and in principle at time, and it is related to this stress tensor and to this pointing vector. One of them is a dynamical thing. Now, if you take this to be equal 0, when is it equal 0? When you have no body. Because what is this f? F is related to, you know, the derivative of the mechanical momentum. So this is like a continuity equation. You see this side of this equation. So what we have here is there is no continuity equation because the momentum is in principle transferred into the mechanical momentum of the body. So there's no momentum can be transferred from two forms. So let us write it now and talk about this a little bit more. We are now interested not in, we are not interested in the force at a point. We still need to do this damn integral in principle, which we will never do. F, the total force, if you remember from the beginning, is now the integral over the volume, right? You remember this? The small f, this f, times d tau, integration over the body. We had this body here, which had this rho, it had the j, inside you have all kinds of e and b's. So we need to integrate. But now, let us look what is happening here. We need to integrate over a volume, and we have the derivative. Now we're going to use the divergence theorem, and because I used it in this course several times, and you saw it also in previous courses, I'm going to do it immediately. So the integral over the volume, let's write it, volume f d tau is equal to the following. Integral over the surface of what? Of the body, for example, but not necessarily. I'll soon come back to this. And then you simply lose this derivative dA, because it's like integration of a derivative, you get rid, and this is the divergence theorem. And now it's very nice, because at least this term, this stress tensor, is on the surface only. What goes inside, we don't care about. It's like all the forces have vanished inside, and only, of course, this integral can be super complicated, only the stress tensor on the surface is taking care and not inside the surface. Not inside the body because of the divergence theorem. And then we have also the second term, epsilon 0, mu 0, that's 1 over the c squared. Here, time derivative, integral s, but here there is no spatial derivative, no divergence theorem, so it's just the integral over d tau, over the volume integral, which means all the volume of the body, whatever that is. But what is s? This is a vector, of course, because f is a vector. What is s up to the speed of sound? What is s here?
It's the
Momentum, but as I said at the beginning, per unit volume. Momentum density. And because I have here delta t, now this is going to be the total momentum. But what momentum? It's a bit confusing. There are two momentums here if you think about it deeply. This is the momentum of the electromagnetic field. So this term is momentum change because of this. This is momentum change, electromagnetic momentum change. What do you mean by change? It's not that I'm changing dollars with the shekel. I mean change in time. EM is electromagnetic momentum change. So yeah, this is the time derivative of the total momentum. And then we can write it using the Newton's law. So what do we have here? What is F? F is the P of the body. This is the total momentum of the body itself. And it's equal to this thing. So what do we see here? There is these stresses, these forces that acting in a complicated way, which change the body momentum, which is acceleration with the usual Newton if the mass is a constant. And these are like forces, but they act only on the surface eventually. They are very complicated because of this T, but they are surface terms. And then in addition you have the change in the electromagnetic energy, which is this guy is equal to that guy. So what is happening here, these are the electromagnetic momentum, and it can be transferred to the body. But if there's no body, then this is simply equal 0, and then you have only these two relations, which is like a continuity equation in a vacuum when the body is not present at all. So yeah, maybe we should write this to emphasize Newton, TdA minus, so what is this? S, this is 1 over c term. What is this integral? This is P electromagnetic ddt. And what is this P electromagnetic? Remember, just for notation, here I had before this P electromagnetic, right? This was momentum per unit volume. This is not momentum per unit volume. This is momentum of the electromagnetic field. Why? Because I integrate over d tau. If I integrate over the tau, it's the total magnetic volume. So this is why I call this P, like you have the P of the body. And these objects are changing momentum according to this formalism. Okay, so this was it, but honestly, I'm not sure that you fully understand what is the stress tensor. Okay, one more remark. So here I integrated on the surface of the body, which kind of makes intuition. My claim was you don't need what is inside the body because all the forces come, some cancel it. And the only thing you care about is T on the surface like you have here. So this is the surface. But as I mentioned before, you can extend it because from the beginning I could, instead of the physical body, I could make it even more distance because the rho outside the body was 0. So this surface I can change as much as I want. Here it's a bit more tricky because here it's actually the volume itself. So let us assume for what we're going to consider now, assume static problems. Which means ds dt equals 0. The complexity will be this t. So I'm going to focus on this term and not about the second term to see what is this t, because this stress tensor is, as I said, it's rather complicated. So I want to explain this a bit more. So the force now is simply TdA on the surface, and this is the surface in principle of the body, but as I mentioned, I can do the integral over this surface, for example, or any surface which has no charges inside and no currents inside. So we assume there's one body, the moon or whatever, and here there's vacuum outside, and I can change the integration surface from here and here. And as I mentioned at the beginning, what is the advantage? Let's say this is far away from us, then I can, in principle, if I know the fields here, in this integration domain, I can do this integral, then I'll get the force acting on the body. So not only I don't need to measure the electromagnetic fields inside and know the currents inside, which are our starting point. The beginning point was we have some J inside the body, some density inside the body, some electric field inside the body, some B inside the body. And now Maxwell is telling us, you want to calculate it, you can work hard. Is there a price? Yes, it's T. T is not a simple thing, but in principle we can do it. So we're going to play a little bit with this and see how it works. So let us just try and explain what is T. What is the physical meaning? And you can see this meaning from this equation. So you remember here I integrated over S and I said it's changing in time, it's like momentum. But now what am I saying? What is this T? So I'm starting from the surface. So if I look at the physical surface, T is essentially the force per unit surface, right? Because you see it's T dot dA on the surface. This is when I think about it when I do the surface of the body. If you want to have a physical meaning to this first per unit surface, and you can think about it as on the surface. And we have two types of terms. One of them are diagonal terms, Tyy. These are called pressures. And the rest, the off-diagonal terms, for example, Txy, Tyz, blah, 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 these are called shears. So if I have Tij, so we have two indexes here, and this is a bit confusing. What is the first index and what is the second index? This is kind of by definition. The first index is the direction of the force. And J is actually the direction of the element, of the surface element.
Perpendicular to the surface?
No. Direction. Yeah, I mean, yeah. Of surface element. So yes and no. The following sense. Here I have T. When I multiply it by A, and you give me the direction, this will translate into the specific direction you are looking at.
Okay.
But remember that this is a vector. So the T itself contains all these directions. It's not that it doesn't know anything about the
surface.
On the surface a priori. But then when you multiply it by the surface, it will give you a specified direction. So J, yeah. So this J is the direction of the surface element. So for example, let us look at this a bit more into depth. What do I mean by this? I have this TdA, right? So we need to think, what is this TdA? It's a matrix times a vector. What is a matrix times a vector? Is a vector. This is because the F is a vector. So what is this thing? What is TdA? That is inside this integral. This is like this: Txx, Txy, Txz, Tyy, Tzz, Tyz, Tzy, Tzx, Tyx. this in principle is dAx. This is already the surface. I'm on the surface. It has a direction. It can be not in the x, not in the y, not in the z direction. So it has three elements in principle: dAz, dAy. And then I need to multiply this. And then what I'll get out, I'll get three elements because the force has three elements. So, for example, what is T, dEA, I want to say, let's say in the x direction, which will give you the force in the x direction. So another way to put this, I write here one integral, but actually if you think about it a bit, there are three integrals here, because there are three components of the force. This is another way to say the same thing. So this TAX is TXX dAx plus, this is TXX, this is just the first, TXY dAy plus TXZ dAz. Okay, so let's assume, so now what is this x here? What is this symbol x?
It's
It gives you
component of F.
the component of x. This is the direction of f, which I said before, direction of the force is the first index. So let us assume dA is dAx. That's simply the direction of the orthogonal. So you see these two terms are gone, and then T dot dA is simply dAx multiplied by Txx. And in this example, this is simply the small f, because I didn't integrate it. Small
Isn't
f
it
times
supposed to be
dA.
plus tyx plus tzx,
What?
because when you
This one?
when I if I cross the matrix with the component when the ay and az are 0, I still have component different than 0.
Yeah, but I'm calculating the x direction.
Only the x direction. Yes.
So only the x direction. Then there is a y, there is a z. Then you're right. Then you will have to have other terms. But what I'm trying to do, the force in the x direction, so let us summarize it. The force in the x direction for an element in x direction, I chose them. I chose it as in the x direction, and the forces in the x direction is given by Txx. So I'll change this to x. So okay, usually this is x, but this is the x. Then if I multiply this by Txx, and I'll get the force in this direction, the same direction of x. This is why Txx is a diagonal tone. It's called the pressure, because pressure is diagonal to the, perpendicular to the wall. The other guys, what are they doing? If you think about them, you have an element, let's say in the x direction, like here. So this is the x direction. This is the way the element is looking at, but let's say you have a force in this direction, which you could have. This will be given by Txy. The force, no, the first one is y. The force, if the force is in this direction, this is the direction of the element. This is given by the force is in y direction, the x is the direction of the element, and this is given by Tyx. So what does it mean? You have a sheet of paper. Usually we think of things bombarding it here and giving a force, which is a pressure, like in a gas. But you can also have a shear, which means that the vector going in this direction, but the force is going in that direction, moving my sheet in that direction of the force. This is all what it means. This is this meaning of this Tyx. Okay, is this more or less clear?
More or less.
More or less, yeah, good. So, okay, so this is the meaning of these off-diagonal terms. They give you forces not in the direction of the perpendicular to the element, but they are inside the plane. Inside the... Inside, so you have a plane, and in principle the force does not need to act in that direction. Here is the force, here is the body. There's no reason why the force will only pull you in this way locally. It can pull you also that way, for example, if you rotate or things like that. There's no reason why it shouldn't be. And this is the physical meaning of these off-diagonal elements of this matrix. Sorry?
Why did they call shear?
This is the meaning of shearing when if you take a body and you push it like that, that is called shearing.
Out of the...
You are shearing is like you have, no, I shouldn't touch this. But if you have a shear force, mechanical shear force, you have a body, you can pull it here and you can pull it there. If I do that to you, you will distort, right? You understand? That is called shearing. So shearing can be also mechanical. If I pull it here, and then it's usually what you do in shearing, you also pull in the other direction, then this body will be distorted. It will, from elasticity, you know this. And this is the same thing because the electric fields can be acting, the normal to the surface is like this, but you can have electric fields in this way, and they are pulling on the top of the surface in one way, and then in the other way they can pull in the other way. Okay? That's mechanical shearing. That's where...
yes, but here we have...
it's not shear from song in Hebrew. It's not...
Yeah. But here the power is only in one direction. I mean, the Tyx, it's not left and right.
First of all, this Tyx can be either positive or negative depending on the...
Yes, but it's only in one direction.
Yeah, but you have also, of course, but you have also Tyz. So you have other contributions. I mean, I didn't plot all of them, but you have all of these guys. So you have all these guys. The elements on the diagonal are precious because they will describe the forces perpendicular to the surface. And then you have two more, altogether three, because we work in three dimensions. I mean, these are three elements. I didn't write TZY, but it's the same thing.
Stop.
So this is the element. It's in the x direction. It has a force up, a force down in the plane, and a force outside of the plane, and that's it. And these are these matrix elements.
We said the matrix is symmetrical.
Yeah.
Why is it necessary that the force in the x direction on the y element will be equal to the force in the y direction on the x element? Why does it have to be symmetrical?
I don't say it has to be in mechanics, but in electrodynamics it is like that. I don't, because of the definition of the fields, because it's AI, AEGA. But I'm not saying this is totally trivial. I mean, it's some symmetry that you have here.
Okay.
But it's specific here to the... So when I had the shearing, maybe you were saying, yeah, I mean, it comes from something. It comes from the electromagnetic field. It's not that you decide how much to push. And there are constraints which come from Maxwell equations. And maybe this is not a good answer, so ask ChatGPT, maybe he will give you a better answer. No, I mean it, but it comes from the physics. It's not a trivial thing, but the physics of Maxwell equations. Okay, so now what we're going to do is we're going to use it in one or two examples, depending on how much time we have, in order that we can just more or less, my aim is not to do anything complicated really. My aim is just to help you understand the definitions at the beginning at least, to solve simple problems. So the simplest problem I can imagine is from electrostatics. So again, there's no S here. And secondly, this is what you learn in high school. You have one charge and you have another charge, and you know the Coulomb force between the charges. So you know the answer. So what I want to ask is the following thing. I have a charge Q, and I have another charge Q, and in between I have a surface. This is my integration surface. Here I have some field x, y, z equals 0. So this is z equals 0. And let us assume that I can measure here the electric field. And we know the electric field. We know the electric field because we know that if you have a charge here, you have some electromagnetic field. We'll soon calculate it. There's another magnetic field, electric field. And then there is some electric field in this plane. And if you want to think about it like this, let us assume you measure it. I measure it. Now, this will be, what will this be? This will be the surface of integration, which is not on my body. And then what I'll do, I will close the surface integration at infinity. At infinity, what is the electric fields there? At infinity at this point is 0. So when I close this surface of integration, which is this surface, the contribution is going to be 0, but there is a contribution from the plane. So what I'm going to do, I'm going to calculate the T, this T, the stress tensor, and after I find it, I'm going to integrate it, and then I'll get the force. Force on what? On the body here. And what is this force? It's trivial, because I know it. It's given by the distance here, and this is just a basic thing. So what I'm going to do here is just to check if I didn't make a mistake or Maxwell made a mistake. But we will gain some insights in what is going on, what is the meaning of these stress tensors, what is contributing here. So immediately, if you have some intuition, what is going to be the most important? You have 9 elements. We're going to find them, or some of them at least. What is the most important one? You see, the force is in the z direction. We know this from basic high school. So we kind of imagine that the most important element will be TZZ. But we will see that. Okay, so that is the exercise. So let us do this as a sanity check. So we want to find, we need to define this distance. Sorry that my painting is very bad as usual. This distance is A, and this distance is also A. So let us write down what is E. The electric field. There's no magnetic field. Now, there is something very nice here, in my opinion. We are calculating, how do we usually calculate the force on this object? We say this guy is creating electromagnetic field here. And this electromagnetic field here, because you have a charge, Q times E, this is the force, right? This is what you do always. But what we are going to do now is different. We are, first of all, it's like that to find a simple thing, but what is the electric field down in the plane? It's a contribution from both. So while we are eventually calculating the force on this, the electric field here is a contribution coming from both terms. And actually the cross terms of the sum of the two electric fields are the important ones in order to calculate this force on this thing. So let us try and do this. First, so what do we need to do? We need to find the fields in this plane and then do the integral. So let me try and plot this. So I'm going to go down to some point here, like that. So let us define the origin, x, y, z. So what is this origin? Is of course exactly this point in the middle, x equals 0, y equals 0. Just here, this is the origin for me. And then I want to plot it like this. From this is A, and then I go down to the plane. So I'm calculating the electric field in this point, so there is some angle, which I'm going to call alpha. There's another angle in the plane, which I'm going to call phi. And this is a positive charge, so what is happening here, if you want to think about it like this is the plane. I don't want to screw up totally, but so if I look at this like that, then yeah, the vector is going underneath the plane, so to say. The force, the electric field is going, continuing if you want. So this is continued, this is just the plane. And then I'm going to calculate, let's calculate the x. We have two components, Ex and Ey. Ez goes by symmetry because both charges are the same. So I need to calculate both of them. And now, what is this Ex? It's very simple. From high school, I need to, it goes down, but then I need to push it up to the plane, and then I need to project it once on the x direction, and the other time to get the Ex, and then project it on the y direction to get the Ey, and that will be just multiplication by sine phi and cosine phi. That would be easy. So all I need to do is add definition. So this radius is r, and then this distance is r squared plus a squared from Pythagoras. And then essentially I'm done with all these definitions. In my integration over the plane, what I'm going to integrate over is r and phi. Integration over all the points in this plane is this integration over r and phi. But if I know this distance, and I know the Coulomb law, then I project up to the plane and then onto the two surfaces. So what is Ex, for example? Ex, and similarly for Ey, is q 4 pi epsilon 0. Cosine 90 minus alpha. The x is the projection cosine phi. And if I'm not mistaken, there is a 2 because there are two charges, one on top and one on the bottom. And cosine 90 minus alpha, that's easy to get. This is just r squared plus a squared power half. And Ey, here I didn't write. And I need to divide, of course, by r squared plus a squared, because this is the distance squared. This is just Coulomb's law. And Ey, if I do the same, is 2, because you have two charges. Q, because it's the same, both the Q's are the same. Sine phi because I'm projecting on y now. This cosine, I'm just plugging it in, then I get r squared plus a squared to the half. This is this cosine here. And then it's actually 3 because I have also this term. And that's it. I think I didn't make a mistake. So this is Ey. Okay. What is, for example, what is Tzx? I claim it's 0. which is related to the symmetry of the problem. The reason is, what is Tij? I mean, if you don't see it, then let me write it. Tij, let us write the definition, is epsilon 0 ei ej minus half delta ij e squared. So if I have zx, then this guy is 0. And here I have the z component. The ez component is 0 in this problem. And then you see that tzx is 0. So there's no shear of this type. Actually, in this problem, there's no shear at all. What is tzz?
Also 0.
Let's see. It's epsilon 0 ez squared minus ex squared minus ey squared plus ez squared. Divided by half. Now it's true that ez is 0, but these guys are not 0. So the tzz is certainly not 0. It's minus epsilon 0 ex squared plus ey squared divided by 2. This guy, we can plug in this guy. And when I square them, I need to square them, you see here. Ex squared and ey squared, which is again related to the density of the energy. When I square them, I have a sine phi squared and a cosine phi squared. This will, when you sum them, this will give you 1. And then you are left with identical terms. So if I do this, I'll get the following. I'll get epsilon 0 over 2 as a minus. Q squared, because of the squares. 4 pi epsilon 0 squared. This is simply this squared. And the 4 is this, comes here. These are this 2 squared, the 2 comes from the 2 charges. And then I have here r squared plus a squared to the power 3. And the power 3 again came from the distance and from the cosine of 90 minus alpha, so you get this strange 3 here. Now I need to do the integration over the plane. So first of all, the yeah, I mean, the tzy is also 0. So why am I caring about the z element here? Z, tzy is also 0. Remember what I said before. The z is the direction of the force. If I'm interested in the z component of the force, I'm interested, the first index is for the force. And in this problem, I know that the force is going like this. Now you can say, hey, that's not fair. Calculate also the forces in this direction. You can do that, but it will give you 0, because I'm not going to do it, but it's obvious. So this is the reason why I look only at these 3 elements. And then I need to integrate over dA. dA is in the z direction, so only this guy anyway will remain. And then I get the final answer. I just need to integrate this thing, which is a complicated thing. And when I integrate this thing, it will be proportional from point of view of A to what? 1 over A squared, because that's the distance squared, because that's Coulomb's law. So if you do that, so let's write at least the integral that needs to be solved. So fz, so I'm not bothering with the x and the y direction, that's why I calculated only these elements, is equal to the integral over the surface, which is this plane, because again, I close everything far away, that gives you 0. this is this TDA. If you want to be specific, it's in the z direction only, because again, this is actually a vector. And this is equal to epsilon 0 over 2. I'm just copying what I have here essentially. And defining, what do I need to define? dAz, I mean, which is easy. With what coordinates? With the r and the phi coordinates. So we have here this term, q over 4 pi epsilon squared. I have here a 4. And okay, maybe you want to write minus 4 at the beginning, which is a bit strange, right? Because why will this give you minus? What is the direction of the force? We know it's up, because they have the same charge. So we have 1 minus here. And then you have this integral. This is the dA, this dA z. Integral from 0 to infinity dr. Integral from 0 to 2 pi d phi, and in the integration I have 1r, because drr is the volume, the element of the, and then I need to copy the rest, which is r squared over r squared plus a squared to the power 3. Then I need to multiply by minus 1. Where does this minus 1 come from? The direction of the A is down, because I'm closing it in the up. If I would close it in the down, direction of the A would be up. Anyways, this minus and this minus is important because this gives you the correct sign of the integral. Now, this integral this integral just gives you 2 pi. And here I have r to the 3 and this integral. So, yeah, we need to look up an integral. Let me give you the integral. The integral is integral from 0 to infinity y to the 3, 1 plus y to squared to the power 3 dy. This is 1 over 4. You can show this. And then the fz, if you do this integral, eventually gives you what you expect, which is q squared over 4 pi epsilon 2a to the power 2, as you expected. So what did we land here? We land here because the force is in this direction. You have only the TZZ coming into play, which essentially is what you expect, and then essentially what we calculated here is a pressure. Now, yeah, so I'll give you as an exercise, a different exercise. So for example, which you also can solve quite easily. So now let us do a second example, which again you know the answer in advance, but still you can calculate this. But it's less trivial, so or different. No, it's not. It's also trivial, but let's assume we have a surface with charge sigma. And let us assume now that the field is in this direction. We add the field E in the x direction. What will happen? What will happen to the body? So this is the z direction, the perpendicular to the surface. Well, I can do that, and what will happen? This guy will go in this direction in principle if it's not stuck. There is some force. What is the force? Well, the force is complicated, but the force per unit area is simply sigma E, let's call this 0, E0 times x. And what do we have here on the, it's very simple. This is simply the charge times E0 divided by the area. The area is this total area which goes to infinity, so this is the force per unit area. What is the total force? It's actually infinity if this stretches to infinity. So this, you know this from high school. Now, I can also calculate now all these t's and get the same result, of course. So what is this, what do we need to calculate? So here, I'll do it kind of quickly or just mention the main ideas. I have P and plus. I have above the surface and below the surface. Different physics. In what sense is it different physics? We have the field in the plane, but we have another field. What is the other field? Because of the sigma. So we have the field of sigma, which you know. How does the field of sigma know? This is again from high school. It goes up here, it goes down here, and it is a constant everywhere. That makes the problem very simple. So we can calculate the electric field, which is a combination of these two fields, one in the x direction, one in the z direction, everywhere in space, in principle, and it will be different on top and it will be different on bottom. Now, eventually we want to calculate the force, which we want to get this result again. Here, eventually we will integrate like that. Take this to infinity, just a little bit above the surface and a little bit below the surface. This is how I'm going to close my integration surface. Doing so, I don't need to bother about the small leakages that I have at the end. So I'm going to, so you can imagine these as boxes that I intend. So I'll have two integrals, one of them from the top. So I need to calculate the tensor on the top, and I need to calculate the tensor on the bottom. And when I'll do the integral, closing this integral over the surface, this is my surface, and I'll have two contributions, one from top and one from bottom. What will happen eventually that some of the contributions on top and bottom will cancel. This is why it's worthwhile doing this exercise. It's not totally trivial here. So rather briefly, what is E plus? What is E plus? This is E on top. This is given by E0. This is the field in the x direction. There's nothing in the y direction. And then you have sigma over 2 epsilon. What is E minus? E minus is E0, 0 minus sigma 2 epsilon 0. What is now Txz, for example, plus? So remember that the Tx, I deleted it, but this element contained Ex, yeah, here. So there is no, this term gone, because x and z are not the same. And then I need to multiply the field in x direction and the field in z direction in the plus, so you see it here. Need to multiply by epsilon 0, so this is, for example, epsilon 0 sigma over 2. And what will be Tx z minus? It will be the same, but with a minus sign, because the field in the z direction is in the minus sign. And this difference is important in this problem. Why is it important? Because when I eventually close the integral, one of them will be in this direction, the other one will be in this direction, and they will not, eventually they will not cancel. This will give you the, this is very important, the fact that here you have a minus and here you don't have a minus. Maybe we should calculate Txx, for example. Txx, if you think about it a little bit, is different. There is no difference between the up and the down. This is because of the squares of, because here you see Ex squared, and here you have only the squares. The squares are not sensitive to this sign. So Txx is, the plus and the minus are the same, on top and on bottom, and they are given simply by epsilon 0, E0 squared over 2, minus sigma squared over 8, epsilon 0 squared. Of course, the epsilon 0 will cancel. Now, if I do this integral quickly over this closed surface, one can show, I leave the details for you, that the total force which eventually I want to calculate in the x direction is going to be the area of this is the total area which goes to infinity. Why? Where did I get it? I get it because I did an integral over this area. So the point is the following. The t's you see here are independent of the position along this thing. And this is because we have infinite slabs. So before, for given r and given phi, we had a different tensor. So when we integrated, you had to do this type of integral. But now they are constant, so the integral just gives you this a. And this is t plus minus t minus in the z element, because this comes up from the fact that we have here these z's here, and this eventually will give you all this in the x direction. If you do this calculation, this f is simply what we had at the beginning, will be equal to the following. This is the total f, so this is going to be equal a t xz plus minus t xz minus 0, 0. You should do this thing, and you'll see that the other elements like these, they cancel out when you do the subtraction on top and on the bottom. And if you plug these two guys in, you'll get, you see the correct answer, which should be simply f equal a times sigma epsilon 0 in the x direction. This first entry is x, the second entry is y, the third one is z, which is the correct answer which we can have here. But what is the message out of this? In this example, what was entering? Eventually was entering these shears. And the reason is very simple, because I put the force in this direction, and in this case you need the shears. Before we had force here and force here, so the force was only in the z direction, and then there was like a pressure, and these two differences create this simple thing. But now we learned one example at least where the shear enters. Now let us think a little bit what happened here. Where did the sigma come from? So, sorry, this is E0. So when we calculate the square of these fields, right? We have the square, E squared, EX, EY. What is going on here? So we have squares and fields, and they come from two contributions. What are the two contributions? The external field, which are called E0 in this direction, and another field that came in the sigma, the second field, and I multiply them. The final result is linear in sigma, obviously, like at the beginning. But what does it mean? It means that in this calculation, we have two fields, one of them depending on sigma and the other one independent of sigma. The cross fields, when you take the square of the total field, the cross fields, sigma times something times E0, the other field, only they contribute eventually. because we don't have here something like sigma squared or E squared. This is in the other terms, but they are not eventually contributing. So only the mixed terms of the fields of the two components are giving you something. And this is something you can expect. Why can you expect? Let us say I want to calculate the tensor, but let's say there's no sigma. Then I will have this term, for example, this term will exist, and the opposite also correct. Let's say I don't have E0, I'll have this thing, I'll have the sigma. But these, if one of these elements, either the sigma doesn't exist or the E0 that is pushing it doesn't exist, then you can have no effect eventually, right? Because there's nothing there. So this means deeply that sigma times E0, that again, in the definition of the tensor, when we square things or multiply components, only the cross terms, again, what do I mean by cross terms? Cross terms between the two different fields are giving you eventually the final result through the stress tensor. Now, of course, all these examples are super simple, but if you have a more complicated object, then this is a good method. And again, I want to remind you that not always do we know what is sigma. Let's say we don't know it, but we can calculate the fields around here. Then I can do the same integrations and get the forces without knowing the sigma directly, but by measuring the fields. So this stress tensor is important for many reasons. Here I talked about static reasons. When I have here this thing, then it is important for a continuity equation for the electromagnetic momentum. So depending if you are coupling this to a mechanical system and getting just the force, and even if this is zero, this stress tensor is entering in many different ways, and it's not a trivial thing, not mathematically and not physically. So please read again and again chapter 8 and slowly digest this. I don't think it's not a trivial thing in my mind, but maybe you think differently. So, okay, I wish you good luck and see you next week. התייעצתי, לפחות לעצמך לגבי השאלה שלך. קודם כל השאלה שלך היא טובה, אפשר לענות עליה בשני דרכים. אחד אתה זוכר על המכיר. אז תשובה אחת זה בפועל השאלה שלך, אנשים חקרו את זה קודם כל.
מה זה?
ויש תשובה סוג של פרקטי ושוב משהו קצת יותר עמוק. אז באופן עקרוני אתה כן יכול